In this topic, we'll start talking about conjugated systems, and in this little presentation, it just covers the nomenclature, properties, and applications of conjugated systems. Let's start by looking at the different definitions of conjugated systems, and this really depends on the location of the double bonds, okay? And so not everything is called a conjugated system. Specifically, a conjugated system is when you have double bonds that are separated by one single double bond, okay? So for example, if you have a straight chain compound, you'll have a double bond, single bond, double bond, single bond, and so on and so forth. In a cyclic compound, same kind of a thing, okay? Double bond, single bond, double bond. So this is a conjugated system. Then you can have what is called an isolated system. In an isolated system, the double bonds are separated by two or more single bonds. So which means the double bonds are far away from each other. So here is a double bond, and then here are two single bonds, double bond. In a cyclohexane system, the double bonds are like this, far away from each other, separated by two bonds. Now in the top one over here, these two bonds are separated by these two or three single bonds, but these are still not called isolated because right here is where you see the conjugation. So as soon as you see alternate double bond, single bond, double bond, that is conjugated right away. And the last definition of the location of double bonds is cumulated. And in a cumulated system, you will have double bonds that are right next to each other. Okay, so in a straight chain, this is what it would look like. And if you had something like this in a cyclic compound, this is what it would look like. These kind of compounds are cumulated compounds. These are also sometimes called allenes. Okay, so you have conjugated compounds, isolated double bonds, and then you have these cumulated double bonds, allenes. Okay, so the nomenclature, a little bit of nomenclature. This is not very different from alkenes, but still just to kind of refresh a little bit on the nomenclature is you have to start the numbering from an alkene, which is the closest to the terminal carbon, okay? And you have to still find the longest chain, and you have, if you have any substituent, you still have to number the substituent and name it alphabetically, okay? So that is still there. If you have two double bonds, you would call it a diene. If you have three, it will be called a triene. And if you have four, tetraene, pentaene, hexaene, and so on and so forth, depending on the number of double bonds that you have. Now, this nomenclature is not based on whether you have a conjugated system or not, okay? That's not what it's based on. It's just based on the number of double bonds that you have, okay? So the double bonds could be conjugated or isolated, whatever it is. We're just talking nomenclature. And then if it's possible and wherever applicable, you should use Ciso-trans or easy configuration nomenclature system. Easy is by far the best one to use. That eliminates all possibility of doubts. Okay, so here is one simple nomenclature. This is 1,3-butadiene. So 1, 2, 3, 4. So 1 and 3. So you take the lowest numbers, okay, as we learned in Organic 1 also. So you take the lowest numbers for numbering for the locations. So this is a butadiene, and this one is a 1,4-pentadiene. So 1, 2, 3, 4 pentadiene. You can start from either side. Your numbering will still come out to be the same. So 1, 2, 3, 4. So again, on the first carbon and the fourth carbon, there is a double bond, and so that is pentadiene, and there are total 5 carbons. Here's a little bit more with more double bonds, so hexatriene and then octatetraene. These two are conjugated systems. Now this one also includes the E and Z nomenclature system, right? And if you remember, the E is when things are on the opposite side, and the Z is when they're on the same side. Okay, so that is when the hydrogens are on the same side, or the lowest priority groups are on the same side. Or highest priority on the same side. In any case, you have the E and Z nomenclature system. Now, the one thing about double bonds that you should remember and not get tricked into this is that if you have terminal double bonds, okay, if you have terminal double bonds, and if you have a carbon, and sometimes this happens also in internal ones, this is an internal double bond, these are terminal ones, and if you have two of the same substituents on one of the carbons, it is neither cis nor trans, or E or Z. Okay, so in this case, the first double bond here and the last double bond here cannot be classified into E and Z because these two hydrogens at the end, they are the same atoms. Okay, so they could be two methyl groups, two chlorine groups, two hydrogens, it doesn't matter. But if you have two terminal atoms, then it cannot be classified as an E or Z, because then there is no way to tell which one is a smaller or higher dominant group, okay, in there. So for terminal groups or even internal ones, where you have similar or symmetrical double bond, you cannot name them E and Z. So don't get tricked. I will trick you. Stability of alkenes, and this is again an important part. This goes to show why we actually have this chapter and why we have to talk about this. Okay, and so there are different kinds of alkenes, and of course alkynes are also unsaturated systems. So you will see alkynes also in this chart over here, and you can see that the conjugated systems over here, these are the most stable of all double bonds and triple bonds, any kind of unsaturation that we have. Okay, so these are going to be the most stable ones. The accumulated ones are the highest energy, which means they're the least stable, and they are least stable. They're very hard to make, and then they're very hard to store also. So then we have cumulated dienes over here. Alkynes are very unstable, very reactive compounds. Internal alkynes are a little bit more stable. Then come the isolated dienes, okay, and then finally the conjugated dienes are the most stable of all the dienes, and that's why we're studying as to why this is, okay, why is it that conjugated systems are the most stable one. The way you will see this in most textbooks is by the heat of hydrogen, okay, and the most heat that is released is going to be by the cumulated diene, because this is the one that has the most energy. Okay, so this is the most stable one. It will release the least amount of energy. Okay, so you will see it as heat of hydrogen or hydrogenation in most textbooks. So one of the things that we have to talk about regarding the stability of conjugated systems is the pi bond, okay, because all double bonds are made up of a pi bond and a sigma bond, okay, as you learned back in Organic 1. So they're all the carbons and double bonds will be sp2 hybridized, and so they have a sigma bond and they have a pi bond. If they have a pi bond, it means that there is an overlap of p orbitals going on. And as we know that p orbitals actually looks like this, okay, where you have a positive region and a negative region. The positive and negative has nothing to do with electrical charge or presence or absence of electron. It is just a wave function, okay? And so right here is the positive region of the wave function, and here's the negative region of the wave function. So in two adjacent carbons, okay, in two adjacent carbons, you will have overlap going on of the p orbitals. Now, when you learn about this back in Organic 1, we really don't talk about this too much, okay? We just say that you have a p and p overlap of orbitals going on, but now we get to be a little bit more specific, okay? Because when you have a p orbital that has a positive region and a negative region, you can have two kinds of overlaps. You can have the positive and the positive region overlapping and the negative and negative, or you can have a positive region overlapping with a negative region, okay? So those wave functions now are opposite. And then here we have the wave functions that are actually similar in charge. So when you have overlapping going on between a positive and a positive region, that is called the bonding MO. And when you have an overlap where you have the opposite regions that are overlapping, that is called an anti-bonding MO, and MO is molecular orbital, okay? Atomic orbitals are when something is not bonded, molecular orbitals are when something is bonded. So here we're talking about bonds. So bonding MO is when you have the similar regions overlapping, and anti-bonding is when you have the opposite regions that are overlapping. And so when you have this kind of an anti-bonding molecular orbital, you also end up forming nodes, okay, in there. So there is one node over here, and then there will be one node here also, okay? And the node just indicates that the positive and negative really are opposite and they do not merge as well. Okay, so the next slide shows it a little bit better for ethene. So here we are, okay, with the ethene, and what you see here is two overlaps going on. Okay, so one here is for the opposite regions. Okay, and here is the one for the similar region. So this one is negative with negative, positive with positive, and then on the top over here is where you have the negative with positive and positive with negative. Okay, here. You can call it destructive overlap. I usually don't call that destructive. I just call it anti-bonding. And so in this case, the orbitals don't really get to merge. Okay. On the other hand, here where you have the positive overlapping with the positive region, you have a nice molecular orbital forming. Okay, and this is again called the bonding orbital, and then this one is called the anti-bonding, because as you can see, there are nodes present over here. They automatically, a p orbital has one node, okay, but then you're forming another node also because of this repulsion between the positive and negative regions. Okay, so this is what bonding and anti-bonding molecular orbitals would look like. So now let's look at the MO diagram for 1,3-butadiene. Okay, and 1,3-butadiene is our smallest conjugated system right here. Okay, and so what happens is that you have the p orbital over here on carbon 1, you have the p orbital here in carbon 2, p orbital here in 3 and 4 also. Okay, so this is kind of what these orbitals look like. So now traditionally when we learn about alkenes and double bonds, we know that the p bond from this carbon and this bond and the p orbitals will overlap here and here and here and here. But in this case, since these bonds are so close together, you will have a general overlap going on from this bond and this p overlap here also. Remember, atoms are very small, and so compounds and molecules, they're very, very small, and so everything is very close by. And so because of that reason, all of these kind of merge and they look as if there is one region, okay, above and below the carbons. Okay, so which means that now the bond length will also change. All right, so traditionally a single bond is 1.54, but in these cases where you have conjugation going on, the bond is a little bit shorter because of this overlap going on, and then therefore this carbon 2 and 3 is pulled closer because of this overlap. And that's why we talk about the stability of these bonds, is because there is so much region for these electrons to delocalize. And this delocalization, okay, this delocalization is what gives stability to conjugated systems, which is not present in isolated systems. So if you had a double bond far away, they would not be close enough to form this kind of an adjacent overlap, okay, between the pi bonds. So anyhow, this is what lends to the stability of butadiene. So this slide here is a little bit busy, okay, but let me explain everything here to you, what this shows. As these are the molecular orbital diagrams for butadiene. We'll start from here. So you have 4 carbons, okay, in the butadiene, and so which means each of the carbon is going to have a p orbital. Don't mind the size, don't worry about it. So just look at the positive regions and the negative regions. Okay, and so if you have an overlapping going on, in which case all the positive regions are on one side and all the negative are on one side, that is the best kind of overlap. Okay, that happens. All right. If you have a configuration where you have 2 on the positive side here and 2 negative on the other side, then you have one node, okay, that forms over here, which means you have half of it that is bonding and then half of it that is anti-bonding over here. That is another possibility. Another combination of orbitals possible is when you have the middle 2 that are on the same charge or same regions, and the last 2, the terminal p orbitals, which are of opposite regions. And so in this case, the middle ones are bonding, but then you have a node between the first one and the third one. Okay, and so if you have 2 nodes here, nodes actually lend to more instability of any kind of a compound. So if you look over here at the bottom one, there are absolutely no nodes here. Okay, so no nodes means high stability, one node meaning little instability. Then we're getting to higher nodes here, and the last one, if you look, is everything is alternate. Okay, so you have a positive region here, positive on the opposite side, and then positive on the opposite, and again positive on the opposite. Okay, so which means everything is anti-bonding, and you end up having three nodes. So one node, two node, three nodes. So by the time you get to three nodes, everything is anti-bonding and it's really high energy. And you're thinking, well, then why does butadiene stay like this? Well, it doesn't. Okay, butadiene will stay for most part like this in most of the most bonding state, the lowest energy state and the most overlap. Okay, with all bonding going on, no nodes forming. This is a very high energy state, and this usually will happen when you have any kind of reactions going on, or when you provide energy to the molecule, then the bonds will start flipping around. Okay, so this is what happens at that point. Here is another diagram just to show you about the energy, okay, of all of these different bonds. So this one is the highest energy where you have the three nodes, and then here is the lowest energy where everything is overlapping nicely, all right? This over here, this line here, the anti-bonding and the bonding line here, this shows you where the electrons actually reside. Okay, and so if you have 4 carbons and you have 4 p orbitals, then the electrons will choose to stay in this region and then in this one. Okay, they will never go to the anti-bonding. So the higher the anti-bonding, the more empty it is. It doesn't mean it's not there. These anti-bonding orbitals are always going to be there. It's just that there's nothing in them. Okay, they are going to be empty. That is the molecular orbital theory. Okay, and so the bonding ones are going to be occupied. We'll talk more about this in another topic also. Now, just to give you a little application of double bonds and conjugated system. Conjugated systems are prevalent in our society, in everything that we do, in nature, in us, everywhere. They're all going to be there. Okay, and so one of the biggest uses of conjugated systems is actually in rubbers. And of course, what can we do without tires these days? That's what tires are made of, is rubber. And chewing gum. Chewing gum is made of rubber too, believe it or not. Okay, and so all of these rubbers, okay, that we have, that are tires also, those are all conjugated dienes, okay, and they're all based on butadiene. Butadiene can be polymerized to give long chain systems, okay, and if you have long chain systems, they end up having more strength, all right. So the polymerization is done naturally, as in natural rubber, and synthetically or artificially in case of artificial rubber. Now, in case of natural rubber, it will have different properties than, of course, synthetic rubber, okay? Because when you're trying to make something yourself, then you can add things to it. But when you have natural rubber, it's a little bit more different. So erasers, for example, those got their start from pretty much natural rubber. And then gum, okay, which is chewing gum, that got started from natural rubber also. And eventually now we are into synthetic mode or artificial mode. So the natural rubber is based on not butadiene. It is a butadiene also, but actually more on an isoprene unit. And an isoprene unit specifically is this kind of a unit, okay, where you have a 5-carbon system, 1, 2, 3, 4, 5 carbon, and you can see the iso is coming from this 3-carbon structure here, and the prene, okay, or the ene indicates that you actually have double bonds in there. So there's no way to tell that you have 2 double bonds in there. Okay, you have to look at the name, the IUPAC name, to figure out that you actually have 2 double bonds in there. But isoprene is the common name for this structure, and everybody knows this. Okay, it's kind of like caffeine. Everybody knows the structure of caffeine, even though it's not an IUPAC name, okay, for it. So in any case, this is the isoprene structure, and natural rubber is actually made from isoprene units. Okay, and so this is kind of what natural rubber would look like. And by the way, natural rubber is a polymer of isoprene units. I think I just said that also. In synthetic rubber, you still have the same kind of a thing, okay, which means you still have the same structure kind of. This is not exactly isoprene, but you still have something going on this the second carbon, and then you still have the two double bonds in here. So in this case, you can see that this is not a simple hydrocarbon anymore. We have actually chlorine in here. So once you isomerize this one, or when you polymerize this one, you end up getting something totally different. And these are neoprenes. Okay, so for example, neoprene you have encountered in your organic labs. These are used as stoppers. The rubber stoppers that we use for most part, those are actually all neoprene. Very strong, very sturdy kind of rubber, and it doesn't really react with a lot of things, okay, which is why we like the synthetic rubber. Natural rubber will tend to react with things, and it's not very stable. It doesn't retain its shape. But once you start getting into synthetic rubber, then it gets a little bit more hardened. So this is another use of conjugated systems. And then we have vulcanization, and no, this doesn't have anything to do with Star Trek, okay? But anyhow, in vulcanization, what they do is they take long chain polymers and they join them with sulfur groups, okay? And what this does, it causes cross-linking between long chains, and that is called vulcanization. And this is very common in tires, okay? And so this produces very, very strong rubber. So Charles Goodyear was the one who discovered this, and of course, who doesn't know Goodyear tires? And so this is really what the structure would look like in the tires. And of course, anyone who has braked really fast, okay, and come to a halt, and you can actually say, as they say, smell the tires, okay, or smell the brakes at that point. And that is actually the sulfur that is released, okay, when friction is caused between the tires and the road, okay. The heat that is produced, it actually causes degradation of some of these bonds, and so you can smell the sulfur in there, okay, and that's what the tires have. And vulcanization is a very normal way now of polymerizing and making rubber stronger. And one other use of conjugation is not really a use of conjugation, it's something that we actually have in our eyes, is of course the ability to see color, okay, and ability to see, and that's a vision thing that's going on in our eyes. And our eyes actually have rhodopsin, okay, which have a whole bunch of conjugated system. When the light hits your eyes, okay, this bond gets transferred into a trans bond, okay? And once this kind of a isomerism happens in there, that's when you start seeing color, okay, in there, and you start seeing things. And this structure is very, very conjugated, and it's also very similar to what we call carotenes. And that's why they tell you that carrots and tomatoes are good for you, because they all have carotenes, and of course this helps with vision, okay, for us. So this is a very simple example of how conjugation affects your vision and how conjugation is important in our life. So from this little topic, please learn what conjugated systems are. It's a very common question to ask you to identify conjugated systems, and learn about the stability of alkenes, another one of those common questions. And then, of course, the molecular orbitals. Okay, so remember how you form nodes and whatnot. Okay, so using molecular orbitals also, you should be able to figure out what alkene is going to be most stable. This is it.